Good morning, everyone. Today I am going to define a definition vector subspace. Coming to the definition, let V of f is a vector space and W is subset of V. Then W is called vector subspace over F if W is itself is a vector space. That is, if we want to say a non-empty set to be a vector subspace of a vector space, it should satisfy two conditions. One is it should be a subset of vector space, and the second one is it itself is a vector space. So whenever these two conditions are satisfied by a non-empty set, then we say that that non-empty set is a vector subspace of a vector space. So once again, what are the two conditions? One is that non-empty set should be a subset of vector space, and the second one is that non-empty set itself is a vector space. Okay, coming to the theorem 1, the statement is let V of f is a vector space and W is subset of V. So then prove that the necessary and sufficient condition for W is subspace of V are alpha belongs W, beta belongs W implies alpha minus beta belongs W. Second one, A belongs to F, alpha belongs W implies A alpha belongs W. So this is a necessary and sufficient condition theorem. So that here we have to suppose W is subspace of V and we have to prove these two statements. And conversely, we have to suppose these two statements and we have to prove W is subspace of V. And the hypothesis in the theorem was V of f is a vector space and W is subset of V. Now I am supposing that W is subspace of V. Just now we discussed the definition of subspace. So W is subspace of V implies W itself is a vector space by definition. Whenever W is vector space, once again W itself is an abelian group. That is by definition of vector space. So now we have to prove these two statements. For that, I consider alpha belongs to W, beta belongs to W. Since beta belongs to W, minus beta should also belongs to W because W is an abelian group, and by inverse property, every element in W having its inverse in W. So that minus beta should also belongs to W. Now alpha comma minus beta belongs to W. Once again, by closure property in W, the sum of these two elements should also belongs to W. It means alpha plus or minus beta also belongs to W. Alpha plus of minus beta is nothing but alpha minus beta should also belongs to W. So that is first condition. So coming to the second condition, we have to consider A belongs to F and alpha belongs to W. Since our W is a vector space, and by the definition of vector space, we can write A alpha clearly belongs to W. So A alpha clearly belongs to W. So we need not to prove A alpha belongs to W, since by the definition of vector space we are having that A alpha belongs to W. So therefore, in first part I have supposed that W is subspace of V and I have proved these two statements. Now conversely we have to suppose these two statements and now we have to prove W is subspace of V. So that I am supposing that alpha belongs to W, beta belongs to W implies alpha minus beta belongs to W. A belongs to F, comma alpha belongs to W implies A alpha belongs to W. So this is our supposition in converse part. Now we have to prove W is subspace of V. So according to the definition, if you want to prove W is subspace, it should satisfy two conditions. Number one, it should be subset of V. That was already given in the hypothesis. Now we have to prove W itself is a vector space. It means we have to prove W is a vector space. So in order to prove W is a vector space, first we have to prove W is an abelian group. So in abelian group, we are having 5 conditions. So one, closure property, second one, associative property, identity property, inverse property, and commutative property. Here, first I am proving identity property because without identity property, I cannot prove inverse property. And without inverse property, I cannot prove closure property. So here we have to prove each and every property with the help of our supposition. So that I am first proving identity property. So I am considering alpha comma alpha belongs to W. Same element 2 times in W. And by our supposition, And by our supposition, whenever alpha comma beta belongs to W, we can write alpha minus beta belongs to W, so that we can write alpha minus alpha belongs to W. Alpha minus alpha is nothing but 0. So 0 belongs to W. Whenever 0 belongs to W, we say that 0 is the identity element in W, and hence identity property holds. So coming to the inverse property, I am considering, since 0 belongs to W, I am considering 0 belongs to W, and once again I am considering alpha belongs to W. Once again, by our supposition, whenever 0 comma alpha belongs to W, we can write 0 minus alpha. By our supposition, we can write 0 minus alpha also belongs to W. So 0 minus alpha is nothing but minus alpha, belongs to W. So the inverse of alpha is minus alpha, hence inverse property holds. Coming to the closure property, I consider two elements alpha comma beta belongs to W. Since beta belongs to W, minus beta should also belongs to W. Since we have already proved inverse property, every element in W having inverse, so that whenever beta belongs to W implies minus beta also belongs to W. So whenever alpha comma minus beta belongs to W, once again by our supposition, we can write alpha minus of minus beta should also belongs to W, so that we get alpha plus beta belongs to W. So if you observe these properties, in inverse property we are using identity element. So without proving identity property, we cannot prove inverse property. And in closure property, we are using inverse property to prove closure property. So without inverse property, we cannot prove closure property. So that we have to prove these properties in this order only. So therefore, closure property holds with respect to addition. So coming to the associative and commutative properties, so we need not to prove those properties, because since W is subset of V, so all the elements in W are the elements in V. So that if we consider three elements in W, alpha comma beta comma gamma, clearly those elements belongs to V, and V is a vector space, therefore associative property holds in W. So therefore similarly commutative property also holds. Therefore W satisfies all the 5 conditions. Therefore we say that W comma plus is an abelian group. Coming to the second condition of vector space, we have to consider A belongs to F and alpha belongs to W. We have to prove A alpha belongs to W. Since by our supposition we are already having A belongs to F, alpha belongs to W, implies we can write A alpha belongs to W. Therefore by our supposition second condition, we can write A alpha belongs to W. This is the second condition of vector space definition. Therefore W is closed scalar multiplication. And next we have to prove the postulates. Once again, here we need not to prove any postulates, because the same reason, since W is subset of V, if we consider any element in W, clearly those particular elements belongs to V, and since V is a vector space, so all the postulates clearly holds. Therefore W is a vector space, and in the hypothesis it was given that W is subset of V. If we combine these two statements, we can write W is subspace of V. Thank you.